Okay. So we're going to start topic 5, and then we'll have some time to work on lab 2. Make sure you write every one of these down. Topic 5. Oh, no. No. Thought I was done with these. Let's, oh, wow, I didn't even hear it. Oh, that's fine. Laplace transform method. We're going to develop mathematical models of circuits, op-amp systems, impedance. We've done that before, but the main one in part 2 is use the Laplace transform to solve for our system models. And we're going to look at different inputs, and we're going to use MATLAB. We're also going to continue with block diagrams, so transfer functions and stuff to be able to simulate this. Now, I don't know all of your experience with Laplace transforms. I just know that when I first taught this class, well, there was actually a time where I was going to teach Laplace transforms and Taylor series for one day. And I was like studying the day before, like, because, you know, my first year teaching, I get behind. And I'm like, what? We're doing all this in one day? Anyways, Laplace transform, we have some tables. So it's not like we're just doing everything by hand. But there's a couple of reasons for it that we'll talk about that can be really helpful for us. So the goal is to solve, like to find, you know, we can approximate that graph, but with the Laplace transform, we can actually solve for that output function. Y is a function of time. Get the whole thing, not just an approximation. That's the nice thing about it. So we've done stuff with transfer functions before. Now, a transfer function is a Laplace transform. We turn all the dots to s's. That's basically that's a Laplace transform. The only thing is, it does not handle initial conditions. If I have a starting displacement or velocity, I can't just create the transfer function. So this is a more formal. It can use all those initial conditions, and then again, just like with our transfer functions, why do we do that? Because it's nice and algebraic. And so it does allow us to move some things around, consolidate, solve algebraically using the complex variable s. And like I talked about, they handle initial conditions. So if I have any starting point, the transfer function cannot work with any initial conditions. So I'd have to do a Laplace transform to actually get that. So where we're at kind of in this ocean, last week we talked about how do I kind of create that graph. This is an approximation. I can take that graph and approximate the model. Now what we're kind of diving into is, we've done transfer functions before, no initial condition. I have one input, one output, great. But if I have some initial condition, I'm going to use the Laplace transform. And so that's what our goal today is, just kind of going over some of the basics, and the next class we'll cover a little bit more in depth. PowerPoint usually cuts off some of my text for some reason. Doesn't like some of these variables. So this is a f, lowercase f is a function of time. You actually don't have to write this down. It is on the equation sheet, but I want to tell you something. I have not ever used this on any of the homework or tests. Isn't that nuts? Now, if you like Laplace transforms, you can start here. This is the actual definition of what Laplace transform. So if I have a function of time and I want to take the Laplace transform, typically we capitalize it. That's kind of what we've been doing with our transfer functions. The definition is the indefinite integral of that function times e to the negative st. So we're taking the integral with respect to time. Obviously, s is a complex variable. It can have real and imaginary parts. What are some other names of S that we've been using when it comes to transfer functions? Like all the S's in the denominator, we can say are the set the denominator equal to 0 are the poles, and the poles are the same as the roots. Okay, and so that's where we can have, my complex roots. I have a real term, I have an imaginary term. Usually we use an A for a lot of the slides, but the inverse Laplace transform. So if I have something in the S domain and I take the inverse Laplace transform of that, that gives me my function in the time domain. So either I go into S's. Why do we do that? It's algebraic. I can move stuff around. I can solve. And then the goal is to always bring it back to the time domain. But if we're not using this, what do we use? And it's on the equation sheet. We have a table. So before I introduce the table, I'm going to just show you how this actually works. You don't actually have to do this on any of the homework. This is just a quick recap of this is what the transform looks like. So imagine I had a function of time, some kind of constant capital A times e to the negative lowercase a t. So if I wanted to find the Laplace transform and the initial conditions are 0, so it starts at 0, here would be the definition. So the Laplace transform of this is equal to indefinite integral of my function, which is a e to the negative at, times e to the negative st time. So that's just using that definition from the last slide. I just want to show you, if we want to find the Laplace transform, obviously we can use this method, but this correlates with the table that we'll show next. So if I've got these, can I combine these at all? These e's? Maybe? Yeah? They're both e to the t. What I like to do is I like to take the constant out of the integral. I don't know if you like to do that. It's one of my favorite things to do with integrals. And then these are both negative, so this would be like e to the negative s plus a times time, something like that. So we can combine them, simplify them. And now what would the integral of that be? Any ideas? It would be negative 1 over s plus a times e to the negative s plus a times time. We're evaluating it from 0 to infinity. Is that what you were thinking? Yeah, because then when I take the derivative of it, then these s plus a's cancel out, so I'm left with that constant. Yeah. Okay, so now I evaluate it from time infinity. So this would be let's see, a negative 1 over s plus a times, now we have e to the negative infinity. So we're setting time in there as infinity, minus e to the 0. So I'm evaluating it from 0 to infinity. That's how we can do it. What is e to the negative infinity? 0. What is e to the 0? 1. Great. So basically, we take all this times a negative 1, and my Laplace transform is whatever that constant is over s plus a. So that is the definition of a Laplace transform. That is how I can take a time-based function and bring it into the S domain. I have my constant, and notice like this A correlates to that A. This one is here. This is an S plus A when A is negative. So we have an e to the negative AT. So if I have a negative AT, that means I have an S plus A. So that's the correlation there. So you don't have to do this. You don't have to do actually any integrals in this class if you don't want to. You don't have to just do all this from scratch. I'm going to show you this is on a table on the equation sheet. So as long as we can use our table, I don't have to do all of this derivation. I just have to try to match up with the table as best I can. So the Laplace transform, this one is pretty easy. Laplace transform of a constant, I'm not going to show you, but that's a over s. So again, we could do the same thing, integral. We would get some kind of constant over s would be the Laplace transform. So here's the table from the equation sheet. Yeah, there's 11 different lines here. So we just did these examples. Notice this looks a little bit different, but for line 6, if I included some kind of capital A, some constant times that, that constant would just show up in the numerator. And so again, all of these have been done for you. You don't have to do it. We're just trying to, jump from one to the other. Let's talk about some other ones. Unit impulse, Dirac delta right here. This is if I'm hitting the input. The input is just a quick hit you take away. So input of 1, that's the magnitude of the impulse. So that's what that symbol stands for. It's a unit impulse. It's a quick hit. The Laplace transform of that is just 1. And again, I could have a constant multiplied. I could have 5 times that. So therefore, my Laplace transform would be 5. A unit step. Unit step is a step of 1. So it's just 1, which is basically the same as line 3. If I have a 1 right here, the Laplace transform is 1 over s. And then we have ramp. We've got a t squared. We see this quite a bit, e to the negative at, something that's dying out. And then we've got sine and cosine. So they're slightly different. Then lastly, we have our a e to the negative at sine or cosine omega t. Now, from our recap right before we jumped into this, remember that our roots are typically looking like this if it's an underdamped system. That, if I can find the roots, that helps my Laplace transform. Because this is your A term and this is your omega term. All right? So putting it into a quadratic formula or solving it with your calculator, and you can do higher order stuff. You can do third order, fourth order, trying to find those roots. That is what's going to help you set these up based on the roots. If I have an A and omega, I'm using these two lines from the equation sheet. If I just have an omega, if A is 0, I'm using lines 8 and 9. And then if I have a real root, I'm using line 6. So we just have an e to the negative at, there's no omega. So the root locations are going to really help you with these Laplace transforms, kind of knowing what's going on. Questions up to this point? Okay, cool. Next slide, please. Oh, if you could pull up your computers, that would be good. I think I had it on the first slide, but we got distracted talking about current events. MATLAB. Now, this is on the MATLAB code sheet. So in Halo, the MATLAB code sheet, which is under class resources, that has all that stuff. We've done some of the things like how to set up an SSR, transfer function, stuff like that. This is down a ways down on that Word document. But it's very easy to do a Laplace transform in MATLAB. So it uses symbolic math toolbox. So if you don't have that, that would be an add-on that you would need. But let's say that my function is 3 sine 2t. So pull up that MATLAB code sheet. You can pull up MATLAB and plug it in. I'm going to solve this on the last slide. If my input is 3 sine 2t, can we solve this? So my function is 3 sine 2t. What line am I using to do the Laplace transform? Yeah, we're going to use 8. So this sine, that means that omega is 2, and I have a constant of 3 that's multiplied by it. So we're going to have a 3. So the function, the Laplace transform, is going to be 3 times. Now I can just use the table where omega is equal to 2. So I get 2 over s squared plus 2 squared, which 3 times 2 is 6. We get s squared plus 4 in the denominator. So using this table, if I have an input, I have a function of 3 sine 2t. That's how I'm using the table. And so that would be the Laplace transform, 6 over s squared plus 4. Now, this will get more complicated. Next class, we're going to talk more about differentiation when I have dots, double dots. How do we go about that? How do we use initial conditions? Today is just kind of using this table, getting a little bit familiar with it for the time being. But that is my Laplace transform. So now that you've got your computers pulled up, hopefully, you have the MATLAB code sheet, or you can just type this in. MATLAB can solve it. So when I'm in the time domain, bless you, we first have our symbolic t, then we create our function, then we want to do Laplace of that function. And this last line is not required, but what it will do, it will make it look like this. Instead of like one line output, it'll make it stand out. Okay? It'll make it pretty. Maybe. Sometimes it's weird. So that's not a required line, but this is how we do the Laplace transform. So we can see it got the same answer as us. Again, sometimes it formats it a little bit differently, but this is one way that when we're doing homework 5 down the road, we can check to see if our answer makes sense, if we may have made an algebraic mistake or something like that. Well, it should be down there, right? Maybe. Go up a little bit. That one. Questions so far? How many of you like Laplace transform? Half a hand. Wait, 2 halves. That makes 1. There are worse things. You're right. You're right. Yeah. Okay. So we can express it with this kind of form. Basically, once I have it in the S domain, anything that makes the numerator equal to 0, those are called the zeros of the transform. Anything in the denominator, any S term that makes the denominator equal to 0, guess what that's called? The poles. So again, it's like my transfer function, right? Once I have it all together, once I have the Laplace transform, anything that makes the denominator equal to 0 is called the pole. Same thing as the root. So again, really helps us understand how the system will operate, what the output's going to look like. So for example, very simple. If this is my Laplace transform, which could be for a very simple system, first order system, S in this case would be -3, would be one pole. And so the time function, if I bring this to the time domain using that table, that would just be an e to the -3t. So based on the poles, we can kind of figure out what the output should look like. Again, we can find an A term, we can find an omega term. So we're not going to mess with zeros that much. What we're really interested in is the poles. Okay. Nice. So what I want you to do, we're going to do a little practice. I want you to find the Laplace transform of this using the table. And then I want you to use that MATLAB code sheet in MATLAB to double check yourself. It will not be very hard. I just want you getting some practice with going back and forth with the table. I will get more. Yeah. What do you do with the 8? That's just a multiplier. So for all of these, with the 2, the 5, the 8, they're going to be multipliers that go kind of like in front of whatever this. It's just a multiplier. Yep. You're just going to carry it over there. Oop. Good. Okay. So let's see. The first one, we just have a constant 0.2. So that would be line 3. That's going to become a 0.2 over S. The next two correlate with line 6. So this is going to become 2 over S plus 3. Notice, again, in this line, we have an e to the negative at becomes an s plus a. Typically, our roots are negative. Okay, so if we have a negative 3, that becomes s plus 3, which means that if s was negative 3, that's my pole. That sets the denominator equal to 0. And this one's going to be negative 5 over s plus 6. Questions so far? Okay, again, this is not the hardest part of Laplace transform, but I'm just trying to build a good base for going forward. Lastly, again, this is a sine, so this would be line 8. So we would have an 8 times, we have the omega, which is 4 over s squared plus 4 squared. So my Laplace transform would be 0.2 over s plus 2 over s plus 3 minus 5 over s plus 6 plus 32 over s squared plus 16. Now, if I wanted to, I could get a common denominator for all 4 of these and then get this big old thing. It would have all 4 of these roots. No, 5. We've got 5 roots here. This is a root, so s equals 0, s equals negative 3, s equals negative 6. Then we have a plus or minus 4i right there. So 5 roots, we could combine it all to get this big thing. We don't have to do that today. Questions? All right, the last major thing we're going to talk about, I think, then we'll do a problem, is the inverse Laplace transform. This is the same thing, just opposite. And guess what? We're going to use the same table. So if I can set up stuff in the S domain, we can bring it back to the time domain. That's the main point. Our goal is to take it into Laplace, do algebra, flip things around, get it nice and simple, and then we can bring it back. This is the process by how we get it back. So in MATLAB, all you've got to change is you're using now symbolic object S. We set up our y equation or our output equation in the S domain. Then we do I Laplace. And again, pretty just kind of changes the format of it. And so if we plug that in, we get this equation right here. And we can look at the roots. The roots are going to tell us this is an underdamped system. We're going to have a negative a plus or minus omega I. And we would find that a is equal to negative 3. So the roots in this case are negative 3 plus or minus 4i. How do I know that? Well, my output has an e to the negative 3t. This is how you do an exponent, by the way. And then we have cosine and sine of 4t. Now, look at these. They're a little bit different. Which one do you like better? You like pretty or the not pretty one? Not pretty. Now it may have gotten better over the years. This is kind of an older. I haven't really adjusted these slides. So you're pretty on this newer version. You know, it's the same. Okay. So this one is kind of interesting because it does combine this. Notice that the 2 is actually over here. This is a 2 times e to the negative 3t. So you got to be a little bit careful with that. So yeah, it does actually give you the same result, just formatted a little bit differently, maybe some combination that you may or may not like. So if I can get everything into the S domain, if I can, you know, again, simplify, move some things around, then we can try to bring it back using MATLAB or using the table. That's our next goal. Is it working? One person says yes. Okay. What I'd like you to do, this is Laplace practice 2. I want you to go backwards. I want you to use the table to find the time function of this set of equations, this one large equation. So use the table, go one at a time. These are like different partial fractions, essentially. And so once we have it all set up, we have our numbers, we can bring it back to the time domain because it matches the table pretty well. And then you can also check it, now that you've got the code up in MATLAB, you can also check yourself after you're done. So I'll give you a couple minutes to work on this. Right now we're on 21. Is anyone staying over spring break to just work on their capstone? Oh, okay. Were you staying around? Oh. It's not pretty? How dare you? 3 squared is 9. Yeah. You could say it's 3 squared. So then you're pulling from here. Then we're pulling from here, here, and here. That should be our 4. So yeah, you turn it up. Some students are saying that pretty is not that pretty. Again, subjective. Is it subjective or objective? Yeah, it is. Okay. Now there were some questions, at least about the first one, which are some good questions because if I am using this line 10 right here, that should be like a 3 over s plus 4 squared plus 3 squared. That would be how it would have to be set up on that end. But I have a 20 up there, so we can multiply this whole thing by 20 over 3. That would be my constant. Yes, 20 over 3. So it's 20 over 3 times this line 10. For line 7, I don't really need a change for that. It's just a 16 times, so the constant would be 16. What would be the constant for this one? 12 over s cubed. It should be 6 because in my numerator there has to be a 2 over s cubed. So that's my constant there. So now bringing it back to the time domain, now since everything is good to go, it matches my table. I have a 20 over 3. Now again, we're going this direction. So now I have an e to the negative 4t sine 3t. I have a plus 16 t e to the negative 11t. I have a minus 6 t squared and then plus 14. So again, you have this table, it's on the equation sheet, it'll be on the test. It's the way that we can go back and forth. Laplace is nice in that we can do algebra. The only time I really need to use it is if I'm trying to find the output equation. What is my output equation? Where I have initial condition. If I have 0 initial conditions, we could just use the transfer function. That's setting up the transfer function. Then from the transfer function, we can still do this part where now we find, those roots. We can figure out how to bring it back to the time domain. So, this is used regardless if we have initial conditions, but the way that we set up these equations will be important to know if we have initial conditions or not. Because one way is definitely faster. But again, the goal is, this is my, you can imagine this is my output equation. So based on the inputs, based on the initial conditions, this is the output function of my system. It's mechanical, electrical, whatever. Questions about these numbers? Yeah. Why is it 20 over 3? Can anyone answer that? He's explaining it pretty well. So I want to match the table as well as I can. This is my omega squared, so omega has to be 3. So for my table, this would be a 3 over all of this to be able to bring it back here. So I have to do, so 20 over 3 times the 3. So the 3's cancel out. I get 20 over that. That's what I get. So you just want to make sure you set it up based on the table. Sometimes I have a constant above. A lot of these are ones, but if they have a constant, that's where I want to be careful with that constant. Ah, okay. Yes, it's got an omega right there. Other questions? Okay. So, a few last things. This is the final value theorem. This is on the equation sheet. So the final value theorem is basically just a quick way, if I am in the S domain, if I've done a Laplace transform, if I have a Laplace function to solve for the final value, or again, this has to be some kind of steady state value. So you can think of it as my output steady state. If I want to find that, there's a few ways to do it. If I have the time function, I can just take the limit as t goes to infinity. That will tell me what that final value is. This is sort of what we've done with DC gain. We set all the s is equal to 0, basically, right? So if we set all those s is equal to 0, that means that there's no change. I'm trying to find that final value using the DC gain. Now this is equal to the limit as s approaches 0 of, if I have that function in the S domain, we have to multiply it by S, then we can evaluate it as S goes to 0. So we can use this to find the steady state value. Now it has to have a steady state. It cannot be oscillating. Otherwise, we will not get an answer. So it does have to be typically like a step input. So it doesn't hold for a sine function, anything like that. Okay. Let's see, do we have an example problem? All right. So let's just show you what it looks like. So this is our theorem check. We're going to calculate the final value theorem if it exists. If it exists. So let's say I've done Bobati. I get to my, this could even be a transfer function. Maybe it has initial conditions. I do a Laplace transform. I get to this function in the S domain. And instead of taking my time, working all the way back to the time domain, using my table and all that, we could just try to figure out if all I care about is that final value, what is steady state value? Again, that would be like F steady state. We can find it from here. Now, this part is really important. If it exists, is there a way that I can tell if this exists? Any ideas of maybe how we can check for that? Because I can do this, take this limit, but it would be really helpful if I kind of knew what I was looking for. Like, will it reach a steady state? If it doesn't, it's not really worth my time to do this. I think they might give me an answer that doesn't make sense. You got an idea? Number on the right equals the number on the limit on the right. I mean, they are equal. Yeah, I would have to get it to the time domain. I don't really want to do that. Is there another way we can figure out like the shape of the graph? Like, will I reach a steady state? Anything like that? Keep making eye contact with students, but then they look away. Yeah, see, it happened again. Let's look at the roots. The roots are going to tell me if there will be a final value or not. If I have, negative real roots, that means that it is going to die out. We are going to reach a steady state. So let's check the roots. What are the roots of this system? This is not something you have to do in your head. It probably, oh, you did it with the quadratic formula? Wow, you're on top of it. You got -1 plus or minus 3i. How'd you do that, Braden? Using what numbers? So you set the denominator equal to 0. That's how you can find the roots of this system. Again, this might not be a transfer function. It's just like my function in the S domain. We set the denominator equal to 0. That's how we find the roots. And this one was a quadratic formula, second order, so you can do it that way. You can use your calculator. There might be higher order stuff. There will be higher order stuff as we go on. But you got -1 plus or minus 3i. Will this system reach a steady state? What do you think? You don't think so? No? The I means it will oscillate, absolutely. But what does the -1 mean? So this means that there's going to be an e to the -1t sine or cosine 3t. So what that means is that we will have oscillations, frequency 3, but with the e to the -1t, that will die out in 4 seconds. Root locations. We talked about it last time in class, where we have different root locations. So if I have a negative real root, that means this is stable. I will reach a steady state value because those will eventually die out, and we could, find the DC gain and stuff like that. But we can use the final value theorem now because we know that the system is stable. We know that it reaches a steady value. We can take the limit. So this is the limit. We're trying to find the steady state value. Now, because I've got this, I'm going to use this part right here. So we're going to take the limit as s approaches 0 of s times my function. So I get a 7s times s plus 3 over s squared plus 2s plus 10. And we're taking the limit as s goes to 0. That's the important thing, is multiplying it by s. We're going to multiply it by s. And so what happens? Well, I can, again, take the limit as s goes to 0. We can expand this out. This is 7s squared plus 21s over s squared plus 2s plus 10. If I plug in zeros for all the s's, this just becomes 0 over 10. That's equal to 0. That's not always equal to 0. This may have been an impulse. So I hit it with an impulse. And with that impulse, it's going to go back to 0. So my final value is this will all die out. It's going to oscillate everything, and then it's going to actually go back to 0. But it's really useless if my system is not stable. If I do not reach a steady state, there's no reason with me calculating this. I mean, I might as well bring it back to the time domain and see what that is, because the roots are going to tell us if it goes to steady state or not. If there's any kind of sine or cosine not associated with an e to the negative value, or if I have an e to the positive value, that means it's going to just keep growing. So those root locations do matter quite a bit. I want you to try one of these, and then I think we'll take a break. You ready? Cool. I would like you to calculate the final value theorem if it exists. What are you finding right now? The root. Very good. If I can find the root, that will tell me, and again, you don't have a lot of practice with this, but the root locations will, once you start understanding these a little bit more, you go, hey, yeah, this is stable, this is unstable. Are we going to reach a steady state? Are we not? And obviously, if we do reach a steady state, we can find that final value. If not, there's no use pursuing any more of this formula. You can actually do these roots in your head, right? What are the roots? S1 equals 0. So I have an S there. If it's 0, it sets the whole denominator equal to 0. I have a second root that is -4. So far, what do you think? Stable? A 0 is great. That means stable. -4 is great. That correlates with like an e to the -4t. So that will also die out. This would just give me some kind of constant, which means I reach a steady state. That's good. But what are the other two roots? Yeah, and I can say it's 0 plus or minus 5i. And what does that correlate with? If this is like a and this is omega. Stable? Stable, unstable. This seems pretty stable. Yeah, well, marginally stable. Now, what this means is that this is going to be like a sine or a cosine of 5t, but there's no e associated with it. There's no dying out. There's no real number. We don't have an e to the negative something t, so that's going to show that it dies out. So what's going to happen is that this graph may look something like this, and it's going to oscillate forever. Now, the reason why is probably the input is probably sinusoidal as well. So if my input is sinusoidal, my output, it may kind of change a little bit. We have an e to the negative 4t. We have a constant here. But then over time, that's just going to continue on with that sinusoid forever. So is there a final value? There is no final value. Therefore, I'm not going to calculate the final value theorem. Only works for a step input, or impulse where I do go back to a constant value. It does not work for a sinusoidal input, which we can see here. So the roots matter a whole lot. I mean, you put that second order equation or that first order equation into standard form, you find the roots. The roots tell you a lot about what's going on. Does this reach a steady state? Is it stable? Is it unstable? What is its graph going to look like? We can get all that information from here. Now, the Laplace transform, which we'll do more in next class, is like I can take all that information, I can bring it back to the time domain and actually get the actual function of this. Like, what is f as a function of time? And it will show me that there is an e to the negative 4t. There's a constant involved, and there is sine or cosine. So all three of them would be part of that equation. So all the roots play a big role in the Laplace transform. Yeah. Oh, I see. Yeah, it would actually be like a sine and cosine 5t. So it's not necessarily repeated, but it's a combination. So like my function here, if I were to take this and do an inverse Laplace, Laplace, what I would get is I would get some kind of constant. That's for the first root. Then I would have some kind of constant times e to the negative 4t. And then I would have like a sine 5t and a cosine 5t. So I can take this based on the roots, and then using this polynomial up here, try to figure out what those are. That's next class we'll talk about partial fraction decomposition, breaking it up, trying to find those constants, because then we could solve, hey, this is my function as a function of time. I've got a lot of different terms going on, a lot of different numbers. And from there, we could also see this doesn't reach steady state. But in our case, we just care, is there a final value? No, there's not a final value because these never die. So yeah, it's a combination of sine and cosine, or you can look at sine plus some kind of phase angle too. Any last questions? This is actually the last thing we'll do today. Sorry. Yeah, we'll have, I thought I had another problem, but this is it. So we can basically take a break and then you can work on the labs. So I will post these, obviously the video, and then it's up to you how you want to use the next hour or so. If you want to take measurements, run some tests. But this was our introduction to Laplace transforms. Basically, what I want you to know is that we're going to use this table a lot, go back and forth. Laplace transform, move stuff around, inverse Laplace transform, and then final value theorem. We'll talk more about how we can use it with Bobati. Like, how do I actually use it with a mathematical model? That's what we're going to cover next class. So we'll do some example problems. Good? All right. Well, let's take a break, and then you can use the time to work on homework, lab, whatever you would like.